from Department of Information Technology, VNRVJIET, here to present our innovation.
Hello, we are from VNRVJIET, Institute of Engineering and Technology, India. Our innovation title is A System and Method to Detect Low Rate and High Rate DDoS Network Traffic. The innovators are Sai Manish, Sai Pranayteja, Rukmini, Akanksha, Raghupati, Radhakrishna and Rajesh Kumar. In the era of interconnectedness and technological advancements, our dependency on the digital networks have never been greater. However, with this dependency comes the threat of cyber attack. One of the most severe adversaries is DDoS attack. Imagine yourself for a moment. The website you're working suddenly stops, leaving you in dark without any information about the services you are seeking. DDoS attack have the power to transform this nightmare into harsh reality. It can disrupt the normal functioning of the network by overwhelming it with a flood of internet traffic. Now, coming to the difference between high rate and low rate attacks. High rate attacks are more severe, which involve flooding the target with an overwhelming amount of traffic, whereas low rate attacks uses small stream of very slow traffic, which are hard to recognize because it is difficult to differentiate between them and the normal traffic, as you can see in the Andrew curve visual representation. DDoS attacks can cause huge loss to the large-scale businesses like e-commerce websites. NetScout's latest threat intelligence report states that 7.9 million DDoS attacks have been occurred in the first half of 2023, making a 31% rise from the previous year. Our idea is to design an explainable machine learning system which fits on significant features identified using the proposed feature selection method. The dataset that we have used is Canadian Institute of Cybersecurity DDoS 2019 dataset, which contains benign and most common up-to-date DDoS attacks which resemble true real-world data in the form of packet capture files. Approximately 50 million network flows are recorded on the training day and 20 million network flows are recorded on the testing day. 12 kinds of DDoS attacks have been performed on the training day, whereas 7 kinds of DDoS attacks have been performed on the testing day. Now, this dataset is transformed into IoT DDoS image dataset. Initially, the packet captured files are transformed into CSV files. Now, for every 60 records, a square matrix generated is treated as a channel. There are 3 channels, red, green, blue. Thus, for every 180 records, an image is generated. This image dataset can be used for image classification architecture models. Several existing systems have used deep learning models to detect DDoS network traffic. Though these models yield high accuracy, they lack interpretability and explainability.
Since the size of the dataset we have considered is 50 million, which is a huge number, we have performed random sampling and sequential sampling to achieve 4 different samples from the dataset. Random sampling holds Gaussian distribution and sequential sampling holds time series distribution. These are the counts that we have maintained throughout the sampling. The size of the trained dataset is 1 million and the size of the test dataset is 40,000. The workflow diagram depicts the overall process of building the system and the method, which contains pre-processing maneuvers, feature selection, and building the explainable model. The proposed feature selection includes initial feature selection and statistical feature selection. In initial feature selection, we remove the features that do not contribute much to the decision making of the system. We achieve this by removing static features, removing single valued features, and discarding the redundant features. These are the final features after initial feature selection. In statistical feature selection, we employ t-test hypothesis testing to identify the significant features. A feature is deemed to be significant if it varies considerably in the attack and benign classes. For every attack class, significant features are identified using t-test. For further feature selection, we have also identified the top significant features contributing to a threshold energy level. For obtaining the final features, the attack-wise significant features are combined and uniquely identified.
After performing the statistical t-test, the design of ensemble model involves in selecting diverse models which uniquely contribute to the overall performance of the system. The selection criteria involves in choosing few models with high detection rate, few with high specificity, and few with high balanced accuracy. The 4 training data samples which were selected are subjected to testing using 4 unique test datasets, and the resulting evaluation metrics are presented here. Among all 16 combinations, the highlighted cells indicate the dataset with high accuracy. The maximum accuracy achieved is 99.3825. The table on the left indicates the results of the proposed system on CIC DDoS 2019 dataset. And the table on the right compares the results of ResNet 50 model and our proposed system on IoT, DOS and DDoS attack image dataset, which is a complete representation of 50 million network traffic flow. The accuracy achieved in this case was 98.64, which is better than the ResNet 50 result. Novelty of our idea is in designing a system which can effectively detect both low rate and high rate attacks with high detection rate. The system can also detect zero-day attacks with high balance accuracy. It is a computationally low cost and explainable system whose predictions are significant at 95% confidence interval. The following are the technical contributions that highlight the significance of our research. The system was developed for implementation on low-cost computational infrastructure. The proposed system not only efficiently detects the low-rate and high-rate DDoS attacks, but also ensures interpretability and transparency in feature selection and model architecture. In this way, we contribute to the field of cybersecurity. Societal impact of our research plays a pivotal role in safeguarding individuals, organizations, and infrastructure, leading to safer digital environment. We can also empower cybersecurity professionals to take informed decisions. Here are some marketing opportunities of our research. Partnerships can be made with cybersecurity organizations to further develop the real solutions from our research. We can also refine our research findings and provide specific solutions to organizations facing cybersecurity concerns. These include providing consulting services like risk assessment and strategy development, etc.
This is the main page of our GUI, which has two options, t-test flow and t-test testing. The t-test flow shows the proposed statistical feature selection method. Here, we need to specify the confidence level among 99%, 95% and 99.9%, and then enter the energy to be retained, and then upload the file. After selecting all the options, we need to click on the Perform t-test button. The initial features are displayed here. The selected features after performing the t-test, the t-observed values are displayed here. The rejected features with the t-observed value are displayed here. The t-critical value at the specified confidence level is displayed here. Here we can observe that the t-observed values of the rejected features are less than the t-critical value. Upon returning to the home page, we have t-test testing, which shows the working of the deployed explainable model. Here we have three options, which are capture eye traffic, PCAP and upload CSV. Upon clicking the capture eye traffic button, a packet analyzer tool CIC flow meter is opened. Here we need to load the ports. As we are using Wi-Fi, we need to select the Wi-Fi port and click the start button. To generate some traffic, I am processing some requests. As you can see here, the traffic is being generated. After clicking the stop button, we can see that the CSV is being saved. Here the raw data of 84 features is displayed. On closing the software, the preprocessed data of 60 features is displayed here after performing the t-test.
On clicking the predict button, we'll be redirected to the results page. Each network traffic flow can be uniquely identified using the flow ID. So we have displayed the results using the flow ID. Here 0 represents benign and 1 represents attack. These are the metrics of the deployed explainable model.
As we can see, our system has achieved accuracies greater than our confidence level, which validates the method. We have achieved high specificity despite having imbalanced data distribution, which is a positive outcome. The system was built on a low computing environment of 8 GB RAM in Python language. To summarize, the proposed method identifies the significant network traffic features which help the system to distinguish between benign and low-rate, high-rate DDoS attack traffic. The future aspects of our research involves further analysis of the flow identified as attack by our system.